Yes, sir. We can see your
Yes. Excellent. Okay, so I'll start because I know you have a limited amount of time. So I think it's good afternoon for you and good morning for me. I'd like to first of all thank you for the invitation to share some of the work that we've been doing on corrosion in the oil and gas industry. And the presentation today is really about looking at some of the methods and experimental and modelling approaches we've been taking to assess corrosion mechanisms in the offshore industry. So I'll cover some examples of corrosion failures, corrosion fatigue and hydrogen embrittlement, and then specifically look at those types of corrosion failure. In terms of pitting and corrosion fatigue, we've been looking at how we might conduct modelling to predict that damage process. And in terms of hydrogen embrittlement, we've been looking at some nickel superalloys, and we've been looking at the effect of mechanical properties and also something called a FRASTA, which is a fracture reconstruction approach to looking at fracture toughness. And I'll finish with some summary comments. So, in terms of offshore, you can see here a cartoon showing kind of both topside above the waterline and below the waterline, where we've got a whole variety of different structures. But also we've got quite a lot of different corrosive environments, and they can range from being aerated as we move towards the top of the sea level, down to de-aerated at, on the seabed. But there's also carbon dioxide, hydrogen sulfide, chloride, and these environments can be at normal or at high pressure and temperature. So there's a whole range of environments that can lead to different types of corrosion behaviour. Here are some examples: pitting corrosion and corrosion fatigue. You can see here some examples of that in some small bore tubing, a pump shaft, and pipelines. And our interest is in looking at how we might predict the corrosion fatigue process, which is a synergistic effect of corrosion and cyclic loading. And you can see here a schematic showing damage in terms of crack length as a function of time or fraction of life. And there are primarily 5 different regimes, and they include pit initiation and growth, which would be considered to be specifically corrosion dependent. And then there's a transition from a pit to a crack, and then following on from that to short and long crack growth regimes, which we would consider to be mechanics dependent. And if we want to determine the number of cycles for that process, we need to include all the cycles that are involved in film breakdown, pitting, a pit to crack transition, short crack and long crack. And the specific challenge here is to define whether what size of defect would be considered dangerous. This is a rendered example of a 12-inch riser pipe, which is showing pitting throughout the section. And interestingly, you'll see that there are pits of different sizes and pits that coalesce or are separate. And our interest is in trying to identify whether a pit might eventually become a crack. So our approach to this, excuse me, is that we electrochemically produce pits on the surface, and then we conduct stress versus number of cycles fatigue tests and look at the failure point. And you can see here in the black circles we have a plain specimen that's without any of the pits in it, and we get a fatigue limit for that material. That's a carbon steel pipeline. If we introduce the pit, in this case the blue dots are at 200 microns deep pit, we see that we get a reduction in the fatigue life and the fatigue strength. And if we increase the geometry, the depth of the pit, we find a further decrease in fatigue life and fatigue strength. And then if we then introduce a second pit, which you can see here down here is an example of two pits that are in close proximity, we see that the fatigue strength decreases further, and if the size of those pits is increased, we get a further decrease. And if the separation distance between the two pits is changed and we bring them closer together, we get a further decrease. So you can see here that fatigue strength is very much dependent upon not just the size of the pit, but the proximity of any other pits to it. So we've been looking at specifically the pit to crack transition, and here you can see our setup where we have a fatigue specimen in the fatigue rig, and if we look through the stereo microscope, we look at the surface, and it's an etched surface with a pit of about, in this case, 500 microns. And our interest is, excuse me, our interest is to see if a pit will, a crack will initiate under a certain set of stress conditions. So I've had problems with this, but what I'm showing here is the camera images of the pit and on the surface, and the digital image correlation maps. What I should mention is that we take a camera image of the surface, and then we fatigue cycle for a set number of cycles, and then we take a second image and we superimpose those two images to look for any displacement on the surface, and that's what generates our stress or strain map. And you can see here, and I'm just going to kind of speed this up. We don't seem to see any damage at the moment, and hopefully, if I can get this, is it going to work or not? I'm not sure. Oh, there we go. So you can see eventually we can see a crack, but if we use the digital image correlation, then what we find is that, if I can, this is just we've had problems with these images. Oh, there we go. So you can see here that as we increase the number of cycles that we started, you can see where the crack is developing, and the strain around the crack increases and increases with the number of cycles. So what we do is we plot the localized strain that we see at the pit surface, the surface of the pit, and we find that there is a gradient change before the point of initiation and before we see the crack. So we define a critical strain for that pit to crack transition, and if we do that, what we do is we find for a given pit geometry, we find the threshold strain, and interestingly, if we change the geometry of the pit, we find that it's pretty much independent of the geometry of the pit, which was a surprising finding for us. And we've done this with a different material, a stainless steel. These are two completely separate studies done in different institutions, And if you look at the stainless steel, again, we get this dependency of strain for the pit to crack transition. So we've started to question whether or not this is an intrinsic material property. But the value that we get for this material is then used in our modelling approach. And our modelling approach is based upon a cellular automaton a finite element model, what we call CA-XFEM. And this is where we represent material and its environment. You can see here, I showed it previously, this is, we generate electrochemically a pit on the surface using a capillary, and that capillary is represented by this, the orange C, and that's an inert surface, so we get no activity there. But where the electrolyte, which is represented by water and different corrosion species, we have a pit generated. So we use this this cellular structure as our starting point. We introduce corrosion rules and diffusion rules, and we generate damage in the surface. We then take that damaged surface, that pitted surface, and we put it through finite element to obtain the stress and strain values. Once we have that, we then go back to our corrosion loop, but before then we assess the strain around the surface, and if the strain has changed, then we introduce a factor which changes the corrosion probability at that site. And the outcome of that is a result where we find pit development. The triangle are the point of highest strain, and we've got two different pits here at different sizes. And you see that the crack does not initiate at the base where we have the highest stress, but it is closer to the surface of the sample where there's a strain localization. And what we also see from this is that it's important to consider the boundary effect and the constraint between the pit, this ligament size between the pit and the boundary, and that does influence the nature of the crack growth. And you'll see that it's very different when we have a much larger ligament and a much higher constraint between the pit surface and the outer boundary. And I'm going to just move this on a little bit, and what we see is that it eventually behaves. So what I should say here is the stress is in the vertical direction, so the fatigue stress is in the y direction, and the crack is propagating perpendicular in the mode 1 sense with respect to that stress. So that's our approach to corrosion fatigue. We can get a number of different pieces of information from that work, such as the pit to crack transition time and the depth at which that transition occurs. But we can also look at boundaries between crack initiation and no initiation, and that it would indicate that if we had a pit of a certain size, for example 140 microns, then the applied stress to be in the cracking regime is above 350. And as you can see, as the crack size, as the pit size increases, the stress required to the cracking decreases. So that's useful information for looking at residual strength effects. There's a number of references that people can refer to, and I can make those available. I'm aware of time, so I'll quickly move on to hydrogen embrittlement, which is just a brittle fracture mode. due to the effects of adsorbed hydrogen, which can be as a result of prior electroplating, of cathodic protection, or just the difference between the corrosion potential between two different materials. And our interest has been in the nickel superalloys, which are preferred materials for oil and gas, and whilst they're extremely corrosion resistant, they do suffer from hydrogen embrittlement. And this has been a long-standing issue. So our approach has been to take a sample. So here we have, get my, trying to get the, there we go. We've got our sample, a slow strain rate sample that's being very slowly extended in a tensile fashion. And we have our solution that's recirculated through the corrosion chamber, and that the conditions for hydrogen embrittlement can change, and I'll explain that in a moment. We have two different types of sample. One where we have the entire gauge section that's exposed to hydrogen, or one where we use our fracture reconstruction approach, where we want to define where the cracking will occur. So we mask the sample, so only this region is exposed to hydrogen. And the effect of that is that in terms of stress and elongation, we see that we have a significant difference between the ductility in air and in a corrosive, in the hydrogen environment. And those environments that we change to look at the effect, and they vary from a hydrogen pre-charged and in situ hydrogen charging in 1 molar sodium chloride with a charging current density of 7.7 milliamps at room temperature. We have an in situ hydrogen in 1 molar sodium chloride, again in the same charging conditions but at 80 degrees C, and a third condition where it's more of an industry standard, where it's in situ hydrogen in 0.5 molar sulfuric acid with a charging current of 5 milliamps square centimetre at 40 degrees C. And what we've noted is that the P1 is the pre-charge, and then situ charging is much more severe than P2. Typically what we see is for our tests in air, a very ductile fracture surface, and then as soon as we move to a different charging environment, we find this embrittled region with kind of quasi-cleavage in the central zones. And what we've done is we've used this FRASTER technique, which is fracture surface topography analysis, to look at the initiation and development of the cracks during that process. So what is FRASTER? Well, what we do is we take our opposing fracture surfaces and we map them with a confocal microscope, and then we use those maps and we superimpose the bottom and the top surfaces. We put them back together, and then where there is a dark image, that's where there is no cracking, and where there's a light image, it's obviously a separation between the two surfaces representing a crack. And this is an example of on the left, it's the nickel alloy sample in the solution. Hydrogen's bubbling away from this. We have an area that's exposed, and on the right we have the stress strain curve developing, and then on the bottom we have the FRASTER showing where the cracks is. Initially you see around the edge of green green circle, that's just an artifact of this, but we have an area to the at about kind of 10 o'clock where there is where the sample is exposed, and you'll see that with the stress strain curve that we're increasing the stress, and we see no activity in the FRASTA map, which is suggesting there's no damage occurring as yet. And so this material, this is a 625 nickel alloy, and it's not until well above yield point that we start to see the damage occurring, and that damage continues to occur across the surface until eventually we get a failure of the sample. And this is just a deconstruction of all the data from the beginning of the test all the way through to the final failure. And what we see with this material, which is 945X nickel alloy, we find cracking occurs very early at the fracture map here, and it's very different to the same material under a different hydrogen charging condition, where now what we see is crack initiation above yield. So it's quite a useful technique to correlate the fracture process with the stress strain curve. We've also used this for looking at fracture toughness, where again we map the surface and interrogate a number of cracks across the surface and look for the crack tip opening displacement, which is related to fracture toughness. So fracture toughness is a function of the Young's modulus, the flow stress, which is an average of the material yield strength and ultimate tensile strength, and the crack tip opening displacement. Now, traditionally, this opening displacement is taken well away from the origin of the crack, and in that respect, we find differences. So we're looking at a local fracture toughness, and we've done that as an example here for a 945X and a 718 nickel alloys, different yield strengths, somewhat different strengths in air, but when we look at the elongation in the environment, we find it's quite low. So what we've done is we've mapped, analysed a lot of cracks on the map, and we get a distribution of the crack tip opening displacements, and hence we get a distribution of the local fracture toughness. And what we see, depending upon how far away we are from the crack tip, a value for the local fracture toughness. So we're kind of suggesting that fitness for service procedures should be very wary of using fracture toughness measurements that are made where the crack tip opening displacement is measured a long way away from the crack tip. And here's further examples in different materials, 945X, 718, 625. And the drawdown conclusion is that conventional fracture toughness, seen here, in hydrogen, for example, it's 148. But if we look at the crack tip, the fracture toughness local to the crack tip, we see that it's something like almost 3 times lower. Again, we have a number of references that are available in the literature for people to follow this up. I'll put this back up in a moment. I'd just like to thank all the people that have contributed to these projects over the number of years, and I will leave you with the summary comments and thank you for your attention.
Thank you, Professor Akid. We are open now to some questions if you have a few minutes.
Yep.
Very good.
Yeah.
Yes,
It's a very
Professor Raja
interesting-
from IIT Bombay, Mumbai, has a
Okay.
question.
Hello.
I Bombay State.
Yeah.
Yeah. So thank you very. We come there.
I'm just getting a microphone to him.
Yeah. Okay.
Can you hear me?
Yeah, I can. Yeah.
Thank you for the very nice work and presentation. The crack tip that you see, the crack is evolving at the mouth of the crack and not at the root of the pit, rather I would say. Right? So, does it happen always, or is it a special case where the crack always happens at the mouth of the pit? Because
Well,
the data that's shown there, it was not, I mean, the typical failure was shown there was not really having that kind of feature. Some of the pits in the beginning,
Yeah.
the field failure, what is shown me where the pit was formed and you saw the crack was sweeping from the front of the pit.
Sorry, let me just go try and get back to.
Yeah, something here.
Right.
Next slide.
This one.
Yeah,
Yeah.
you see here the crack
Okay.
is radially growing.
Yeah.
So
Yeah.
the model that you're proposing is that the crack is at the mouth of the pit, not at the root of the pit.
Yeah.
Is that
Yeah.
something specific to the model that you have? Or
Right. Well,
and second
yeah.
question
Well,
is, the pit is always not necessarily hemispherical many times, right? The
That's
pit
true.
also
That
can
is-
be then. In which case, how does this crack growth
Yeah.
take place? Yeah. Thank you very much.
I completely understand. So what I should have shown was another map. Is that initially what we find is, can you see my arrow on the image?
Yeah.
Yeah. So initially what we find is that the crack kind of develops each side, and then eventually grows until eventually it grows into a semicircular crack. So we've seen that the strain localization is occurring in these regions where the crack initiates, and eventually these cracks develop until they become what we call a classical hemispherical fracture mechanics and crack. So yeah, sorry, probably I should have had an extra image on here to show what we've seen in some of our studies. Your comment on the profile of the crack is absolutely correct. What we've done at this stage, obviously, is try to. One of the things that we did do was we did not try and use any mechanically deformed hits, i.e. from drilling or from electro machine discharging, because they're not representative at all of the pits. So these pits are generated electrochemically, so they generate and they produce quite a kind of rough surface on the inside, and that is different to the modelling of a smooth hemispherical defect, and we've noticed that. But you're absolutely right. What we've done at this stage is just we've taken the first step towards trying to develop a model with this type. What we can do with the model is we can change the shape, and it's not really until you get to a very, very deep, narrow pit, that you start to see that localization move from the surface to the bottom of the pit. But I take your point about changing pit profiles. Yes, that will have an effect. I hope that's helped.
Professor Akid, we have another question, if you don't mind.
Yep.
You can.
Yeah.
Professor Akid, am I audible?
Hello.
Hello.
Yeah,
This is Professor Lakshman from
IIT Madras.
IIT Madras.
Professor,
Mhm.
yeah, am I audible?
Yeah, good.
It's a very interesting and very nice presentation, Professor. It's a privilege to be here to listening to your talk. I just have one query, probably because of my ignorance, I didn't understand it. If I assume that you made a pit by a capillary tip, right, and then
Yes.
you took the dried surface for fatigue studies, right?
Yes.
But in your real life, you always have the possibility of electrolytes seeping in, the repassivation aspects coming into picture. How
Yeah,
does that
yeah.
would change your model? That's the question.
Yeah.
Thank you, sir.
Yeah, I completely agree. One of the big problems is trying to do the digital image correlation with a liquid between the surface and the camera, because you get distortions. We have done some tests whereby we have generated pits and then continued to do the fatigue cycling within the environment and looked at the lifetime. But these studies initially are here to what we might represent as a passivated pit, such that it's the defect that's causing the issue rather than any continued corrosion. What our next stage is, but we do actually include this in the model, is that corrosion is always taking place, but if the crack growth is faster than the pit growth, then we get continued cracking. If the pit growth is faster than the cracking, then it subsumes the crack itself, and it delays the onset of cracking. So you can, in the model, you can change the probability of corrosion, and we have done this in other studies where we were looking at intergranular corrosion and the effect of it's on aluminium alloys, the effect of a surface oxide film. And if you increase the surface oxide film, what you do is you delay the onset of the intergranular corrosion. So you can, and this is, I guess, the benefit of modelling, is that you can play around with the parameters of the model to try and affect what we might be seeing in a real service environment.
Thank you, Professor Akid. My name is Sundar, and we have one more question.
Yeah.
I thought I would use my chairmanship privilege and ask you a question myself, but there's
No
one
problem.
from the audience. I'll let that go first.
Okay.
Perhaps while he's coming up, I have my question is, like we have the Kitagawa Takahashi diagram in fatigue, for fatigue crack
Yeah.
growth.
Yeah.
Would you look at constructing such a diagram so that we can come up with a corrosion pit or corrosion crack depth that is acceptable from a static fracture viewpoint?
Okay. So we have published a paper. I had a researcher when we were looking at some work with submarine shaft rotor shafts, and the researcher and I we published a paper which shows a Kitagawa plot for both in air and corrosion fatigue, and I can happily provide you with that reference.
Oh, wonderful. Thank you. Oh,
Okay. So we have actually published the effect of corrosion on the Kitagawa plot.
yeah, there's one more question coming up for you.
Yeah.
Hello. Sir,
Hello.
am
Hi.
I audible? Yes. I'm working in nuclear industry, so a lot of time we have issues where cracks are found and we have to demonstrate fitness for service. And
Right.
at the present, we demonstrate it by using fracture toughness, which are based upon either linear elastic fracture mechanics or elastic plastic fracture mechanics. So at
Yeah.
the end of this presentation, you have mentioned that we should be wary of using the fracture toughness which are based on away from the crack tip.
Yeah.
So, sir, can you explain why we should not use those approaches? Because we use ASME section 11 where it provides a method to analyze those defects and demonstrate how much remaining life is there.
Yeah, I think what the work that we did highlighted that there is a possible risk of conservatism if you use a fracture toughness that's measured where you have the crack tip opening displacement well away from the actual crack tip. I think we have, and you might argue the case that if the fracture toughness that was predicted using the standard method, then you wouldn't expect any failure in our materials. But the fact that we get failure below a fracture toughness that we kind of predict suggests that maybe we're being over conservative with that fracture toughness, and it's really the fact that it's what's happening at the crack tip, and the closer that we can get to that crack tip, that I feel I may be wrong. I'm happy to be wrong. If someone can tell me why I'm wrong, then I think we should be perhaps looking at what might be a less conservative fracture toughness value for materials in given environments. But that's very much open for debate. And I recognise that this is more of a research kind of approach rather than a standard industry testing. But at the same time, it's not a particularly difficult thing to do, the FRASTA. If you have a confocal microscope, it's been used for many years. So it could be that what we need to do is to start looking at local fracture toughness measurements rather than what I would consider macro fracture toughness values.
Okay.
But, no, I may be wrong.
Okay, thank you.
Okay.
Professor Akid, thank you very much for your patient response to the questions, apart from a brilliant
Yes.
talk that we heard from you.
Yeah.
We have 5 more talks in this session. You're welcome to stay back, but for now, may I
Yeah.
request you to unshare your screen, please?
Yeah, I'm.
I know you're
I'm
busy
no-
and you have another engagement.
I've got to examine now some student presentations.
I hope we have
Well,
left
that-
you in a good mood and you can treat them right.
Well, it's the computers that leave me in a bad mood. It's not the people, it's the computer. But I'd like to try and join tomorrow, but I just have a feeling that I had this problem with the Google Meet, I'll see if I can resolve it, and maybe try and join you, have a discussion on collaboration and research activity tomorrow.
Professor, Professor Akid, this is Shamasundar here. It was very nice. Thank you very much. We prefer you join tomorrow, especially regarding this fracture toughness issue, and maybe there is a case to take to ASME as a code case. Maybe we can take this up tomorrow. I don't know if you have attempted that. That's beyond the scope of today's this session. Tomorrow maybe we can discuss if there is a scope to take to ASME Section 11 committee as a code case for changing the method of how do we treat this fracture toughness. No? That's a possibility.
Okay.
Thank you. We will share you the link, and maybe you can share your Zoom link for tomorrow's meet. I will send the
Okay. Right. Okay. I'll try and do that.
Okay. Thank you.
Okay. I'm going to end the meeting now. Okay.
Thank you.
Okay. Thanks. Thank you. Bye bye.